Let us start this lecture with a thought process that excess of information degenerates the strength of mind due to the generation of excessive entropy that we all experience in modern world, because we are bombarded with the information. And of course, we are discussing about basically the thermodynamic where entropy comes into play, and it is also true for our life. And if you recall that we were discussing about the Rankine cycle, and rather ideal Rankine cycle, and we discuss in the superheated steam table. And we will be taking an example and then see that how you can solve the problems by using the principle or the analysis procedure we have discussed in the last lecture. And so, then question arises how to increase the thermal efficiency of the Rankine cycle. What are the ways and means? If you recall that when we are discussing about the Carnot cycle, I had told that you can increase the thermal efficiency by increasing the source temperature, right, or by decreasing the sink temperature. So, that is the way where we can increase the thermal efficiency for the Carnot cycle, and similar way also we can do for the Rankine cycle. So, and let us explore how many ways we can enhance the source temperature. In this case, Rankine cycle is the boiler temperature, like how we can increase, what are the ways? Any idea? We have already done that, like if you look at like we have superheated, use the superheated steam, that is the superheated Rankine cycle, right. Instead of saturated steam, right, we have enhanced the temperature from saturated steam for a particular pressure to the superheated steam for the same pressure, right. That is one way. We can also increase the what you call the pressure of the heat addition in the boiler, we can increase, right. And by that we can also increase the temperature. As I told that we can use this superheated steam, and if we will do that superheated steam, like of course, if we are operated from 3 to 4 and expanding, we may have facing some problem, right, of the quality of the steam being less than 0.9, then we are having problem. But if I will superheat it further, right, from 3 to 3 dash, what will happen? And it of course, the temperature of the what you call boiler will be higher, and also the steam will be entering into the turbine at a higher temperature. So, question arises whether it can take that temperature or not, depending on the material being used both in the boiler and the turbine. Of course, the turbine is more critical because it is a rotatory element, rotating system. So, therefore, it will be having not only the centrifugal stress, but also the thermal stress one has to take, the turbine blade has to take. But however, if I do that, let us say material available, which can withstand high temperature, then if I will expand from 3 dash to the 4 dash, what happens? That my there is a change in the quality. If you can look at, this is one quality, quality, this is 4 dash is closer to the saturated line, saturated vapor line. This is your saturated vapor line, right. So, therefore, quality will be improved. That means, you are basically winning in the both the side. It is a win-win situation, right. As a result, what happened? The work output has been enhanced. If you look at this portion, the work output, is being enhanced. Apart from this work input, right, that is this portion, right, there is a additional here. there is an increase. Therefore, work output will be getting higher and thermal efficiency also will be higher, and also the quality problem being solved or being improved, like. And as I told, the quality of steam at 4 dash is greater than the quality at steam at 4 state 4. So, therefore, the quality has also improved. So, question arises, how far we can go on increasing the temperature 4, the maximum temperature, temperature 4 state 4 means the maximum temperature, right. There is a limitation of, that is metallurgical limitation, that is the like being done, because it is generally restricted to the 600 degree Celsius. That means, it will be less than equal to 600 degree Celsius as of now, but tomorrow maybe better material will be what you call available, and then one can go for higher temperature, like that way. So, and as a result, if the temperature is higher, the source average temperature has been increased, because of you are going for higher temperature T 4. And P, another way of going for is that you increase this boiler pressure, like if you increase that pressure. So, what will happen? This is coming over here, of course, keeping the temperature same, because there is a limitation. So, that limitation is that I cannot go beyond 600 degree Celsius. So, therefore, if I keep, what I will do, there is another way that you can increase this boiler pressure, right. And but then there is a problem, if you do that and keep this temperature, then again you land in the problem of the quality 5 dash. Quality 5 dash is basically away from the saturated vapor line. So, therefore, this will be lower than the 5, x will be lower than the 5. So, then you will have to learn how to handle, you will have to handle how to overcome this problem. So, as I told that 5 dash, that lower quality of the steam, that means more moisture will be there in the steam at the 5 dash as compared to the 5 state 5. So, the corrosion of turbine of the blade will be occurring, and that is the problem one has to look at it. So, there is another way of going by that if you go on this pressure, right, if I go on increasing the boiling pressure, I can reach a point, critical point, right. If I increase that critical point, then like it will be go directly, the liquid will be converted directly into vapor. This is your superheated vapor region, right. So, that what happened, I can compress this and then go directly into the 0.3 and then expand it, of course, depending on, I can go for a little higher temperature, for a particular pressure, if you look at, and that is advantageous of using that. Of course, for that you should have a better material and other problems will be there, and this kind of Rankine cycle is known as the supercritical Rankine cycle. Of course, we are considering ideal, therefore, it is a supercritical ideal Rankine cycle, and nowadays the people are using under this condition. So, if you look at, as a result, its thermal efficiency is quite higher as compared to the superheated Rankine cycles. And if you look at the critical pressure is 22.09 megapascal, but nowadays people are operating around 30 megapascals. In India, we are having a few of the supercritical what you call power plant, particularly recent one, but the numbers are very less, and we are basically importing this technology. We do not have our own, and I wish that some of you will work and then do develop a better power plant and design basically supercritical. And of course, there will be an increase in work input in the pump. So, because it is going for the pressure, right, higher pressure. So, naturally the work input to the pump is will be much higher as compared to the superheated steam power plant, right. So, that of course, I mean like because one has to pay this thing, and so also the pump will be bulky and then cost will be higher, lot of other problems comes into pictures. So, how can we increase the thermal efficiency without increasing the maximum temperature, right, because as I told there is a metallurgical limit. Limit is for the timing it is 600 degrees Celsius, we cannot go beyond that. But then question arises how we can increase without really increasing the temperature, maximum temperature, right. So, what are the ways? Any idea? So, as we discussed that we can use a high boiling pressure, right, that is one way of doing it. And another way is reheating the steam while avoiding the problem of excessive moisture at LPT. That means, we will basically will be expanding the gas to certain extent, maybe in the superheated region, then reheat it and then go to again the maximum temperature and again expand it, so that we can overcome the what you call the problem of the moisture in the at the end of the expansion. So, if you look at a typical reheat cycle system is shown here. In this case, what happened? This is a boiler, right, and there is a turbine can be divided into two categories. I mean like two portion. One is high pressure turbine and this is a low pressure turbine. So, in the first what will happen? It will come heat being added in the boiler, it will come to this high pressure turbine, that is 4, and then it will be expanded. Once it is expanded, it will go to boiler again and get heated up and come to the again expanded in a low pressure turbine, and it will go to the condenser, and then after that of course, it will go to the pump and go back to the boiler, right. So, that is known as reheating. If you consider this thing. So, what is happening? It is coming over here like the boiler, then it will go to the what you call turbine, and the expansion 4 to 5 is basically in the what you call high pressure turbine, right, and 6 to 7 is basically low pressure turbine, and this portion what you call this portion is reheating. 5 to 6 is nothing but your reheating. You are heating again to the maximum temperature, that was the T4 is equal to T6, you can think of ideally like that way. So, what you are doing? You are reheating. As a result, what is happening? You are getting expanding the gas in the low pressure turbine to X7, which is closer to the saturated vapor line, right. And if it could have not done, then what could have? It could have happened in this way, that is it could have expanded in this, right. If I say this is 7 dash, that means the quality of X7 dash could have been very less than X7, yes or no. If you say that X7 is 0.9, X7 dash will be definitely less than 0.9, okay. It will be maybe 0.8 or 0.75. So, that the moisture content at this point without reheating could have higher, and then corrosion could have been more, their problem would. So, if you look at not only you are what you call avoiding the problem of the moisture or the quality of the steam, but you are also adding heat here. So, that what happened? The average temperature is again increasing, you may get some higher thermal efficiency. So, we will basically it is a win-win situation, we are getting higher thermal efficiency and higher quality of the steam, right. That means moisture content will be less. So, and let us look at how we can analyze this problem, that is total heat added per unit mass will be equal to Q in, what is that? This is from H4 to S2, this one, right, Q in, and also the heat added here, this is also Q in, H6 minus H5, this is heat added, this portion is heat added, addition, that is from H5, H6 to H5, right. This addition is from here to here, this portion, that is your Q in. And heat rejected as usual, that is Q out is nothing but your H7 minus H1. So, the thermal efficiency you can say that this is Q in minus Q out, right, that will give me the net work output. If you look at this portion will be give me what? Net is equal to W turbine minus W pump, yes or no? Okay. So, that is nothing but your Q in, we have seen H4 minus S2 plus S6 minus H5, of course, this is your nothing but your Q in, and S7 minus H1 is Q out, and divided by the Q in. So, the single reheat system in modern power plant can enhance the thermal efficiency 4 to 5%, which is a quite a bit. If you like increase your thermal efficiency by 1%, it will be, because the power plant is a very order of megawatt, right. So, therefore, people strive to get even 1%, means they will be very happy, and 4 to 5% is a quite a good concept. So, several stages of reheat system can be used in large power plants. It is not only the one, but several, but of course, it will be having diminishing return later on, like you will use. So, multi-stage kind of reheating cycle, if you look at what will happen, I can reheat here, I will take this here and then reheat here, again go on doing that. So, then what will happen, this average temperature will be go on increasing. So, that it will be temperature will be kind of things. So, that of course, you can get a steam at the end of the expansion, which is almost one can think of getting a saturated vapor, kind of one can get ideally at least. And this efficiency will be much higher as compared to other. Question arises, how many stages of reheating stages one can go for it. So, generally people what to call whatever the efficiency you get using the single one, the first one reheat, if you go for the second one, you will get the half of that. Let us say if it is 4%, like in the first one you are getting, then in the second reheat system you will get around 2%. It is not exactly, but around that, there is a ballpark number. So, if you go for the third one, again it will be reduced the efficiency, so that you will get diminishing return kind of things. So, therefore, number of reheating system in practical power plant is restricted to only 2, because if you are adding, it is a more extra, like you will have to reheat and then piping, lot of cost is involved in that. So, let us consider an example, like in a thermal power plant operating in a reheat cycle, steam at 50 bar and 500 degree Celsius. This pressure is given 500, I mean from here itself one can say that it is superheated steam, right, it is not saturated. Enters into a high pressure turbine and leaves it at 10 bar, right, and the steam is reheated back to the 500 zone, that is a restriction for this power plant. Before being fed into low pressure turbine, condenser is maintained at 0.05 bar, right. Generally, of course, in this example 0.05 bar, people use 0.7 bar for the condenser. Why they cannot go beyond 0.7 bar? Because there will be leakage problems, like the low pressure, there will be leakage problem in the condenser. So, but in this example it is 0.5 bar. So, estimate the thermal efficiency of the power plant and the amount of steam for the 20 megawatt power plant and quality of the steam at the exit of low pressure turbine. So, we need to find out the thermal efficiency and m dot, that is the T, and x 7. So, if you look at, we are basically to find out this x 7 here, what it would be after the expansion, and this temperature basically given as 500 degree Celsius, and this is at 50 bar. If you look at, this is 50 bar, and this pressure, if you look at what is this pressure, this is also constant pressure line. What is this pressure? This pressure corresponding to 10 bar, and this is corresponding to 0.05 bar, right. So, we will see that how we can solve this problem, like of course, we need to find out thermal efficiency, and which is basically H 4 H 4 by H 5, that is your turbine work, right. Okay. This is high pressure turbine H 4 to H 5, right. This is your high pressure turbine, yes or no, and S 6 S 7 is your low pressure turbine, work done by the low pressure turbine, and this is H 2 minus H 1 is your pump work, and then Q in is given, basically it is in two cases, one is H 4 minus S 2, this is in input, right, and S 6 minus H 5 here, this portion heat being added, right, Q in. I can say this is Q in boiler and this is reheater, you can distinguish it. Okay. It is a boiler first and then again it is going to going there. So, I need to have, so if you look at, I know this portion, right, the temperature and pressure. So, therefore, I know this H 1 from the what you call superheated steam table. Do I know this enthalpy at the station 6? Yes, we know, I mean from the corresponding to the pressure of 10 bar and 500 degree Celsius. So, superheated steam at 500 bar we can get H 4 and entropy we can get, right. We can also other properties which I have not mentioned here, right. From the saturated steam table at 10 bar, right, we can get all these property Hg, Sg, all those things we can get. And from superheated steam table at 10 bar and 500 degree Celsius, we can get these properties S 6 and S 7. H 6 the enthalpy at station 6 and entropy at station 6 we can get corresponding that. You may be wondering why we need to data of the steam at the 10 bar, right, saturated steam table. Why? Because we do not know actually this point, right, H 5 we do not know. It may be superheated, it may be here also, it may be in the wet mixture region, right. So, therefore, we need to know that. So, of course, from the saturated steam table corresponding to 0.05 bar you can get Vf and Hf, all those things you get, and keep in mind that this is nothing but your H 1 here, H 1, and you can get Hg, this is corresponding to Hg here corresponding to 0.05 bar, right, and here basically and if you look at this is Sg you can find out, and this is that, like and we can get this how much enthalpy S2 minus H1 nothing but V delta P, and this is corresponding to, this is basically corresponding to basically Vf1 you can say, right. And the pressure the difference pressure, one is 50 bar, this is your 50 bar and this difference, right. Calculate and then you can get this H2, because we need to find out how much heat in. Similarly, in the for a high pressure turbine, we know that entropy at station 4 is equal to entropy at station 5, because of fact that this is an isentropic expansion, right, that is 4 to 5. So, and we found that that S4 is equal to S5 is equal to 6.97 kilojoule per kg Kelvin, which is greater than Sg, that is 6.85. This is basically kilojoule kg Kelvin, right. Therefore, it is a superheated steam. In some problem it need not to. Okay. If it is in between, suppose these values S4 is less than 6.5862 in this case, then it could have been having some quality or the kind of the wet mixture, it is not a vapor. So, it will be that, but in this example it is turns out to be superheated steam. So, if it is superheated steam, therefore, you will have to find out what will be the temperature, right, and then because you need to know the temperature. Superheated steam pressure is not good enough to find out. By linear interpolation, you will find out that what it would be the kind of entropy that we have done, we will not repeat it, and you will get the temperature. Once you get the temperature, then you will find out what will be the enthalpy at station 5. So, from the low pressure turbine, right, also the similar one, that is S6, this is your low pressure turbine, right. The expansion process is isentropic. So, therefore, S6 is equal to S7, right, S6 is equal to S7, and we know this what you call S6 is known to us, and so also the S7, and Sg is known from the corresponding to 0.05 bar, and Sf is known. So, we will find out X7 is happens to be something 0.92. Okay. So, once you get this quality X7, then you can easily find out what will be the enthalpy. So, then enthalpy would be basically you substitute these values and you will get, right, this is your what you call X7, right, and the net W net, we will find out H4 minus H5 plus H6 minus S7. This is basically what you call high pressure turbine, and then work, and then low pressure turbine work minus the pump work, and you will get 1563.86, because all these are known, right, 67 S2 H1 already we have evaluated. So, you will find similarly you can find out Q in, and Q in having two components, one is the boiler H4 minus S2 and S6 minus S2 is the reheating portion, because you are reheating it steam. So, that all are known, H5 is known, H6 is known, and S2 already you have evaluated, H4 you know. So, you can calculate that 3793.78 kilojoule per kg. And from that you can find out the thermal efficiency, because we have already evaluated the net work output and net heat input, and then it happens to be 41.2%. If you look at, if you want to reheat, you will find that like it is lower than that, and we know the power, that is 20 megawatt, right. And if we know the work specific the work in net work output from this system or for this power plant per unit mass, then you can find out the amount of steam is the 12.79 kg per second. So, we will stop over here, and we have seen that how you can use the reheat cycle and how you can solve the problem. In the next class, we will be talking about the regenerative systems, where you can utilize the heat which is being rejected by the condenser. Thank you very much.